Optimizing Fin Arrays by Using the Principle of Natural Selection by Carson Lockridge and Josh Mayberry. The goal of this object was to create a modular optimization program that could create the best fin array. The main section of the program is a genetic optimizer. This means that it mimics the theory of natural selection, which is that in a given population, only the best will reproduce. Because of this, future population steadily gets better and better, and the program this selection of the best is called fitness, how well an individual of a population fits the goal conditions. The fitness function loops through each individual of the population and determines how well each fitness fits the various goal conditions. The fitness for each individual is then given to a function that determines which individual of the population best matches the goal criteria. Each individual is then treated as a chromosome. Individuals are paired up and their independent variables are switched the same way that a chromosome of a mother and father mix and mutate. Here's an image to help illustrate the way this works. Step 1 shows that 4 individuals will have children. In step 2, their chromosomes are paired and switch pieces of themselves around. In step 3, it is shown that random mutations can happen to mixed chromosomes. This function is used by another function whose job is to follow a population over time and determine when they have become good enough. And this function in turn is used to be yet another function whose job is to follow an entire world that contains various civilizations. The reason why this function is important is because the population might converge on an optimum that is local instead of global. In order to do this, the program creates several randomized populations which meet and mix. This process is repeated 14 more times. The overall best is then shown to the user. This makes the chances of finding global optimums much greater than they would be otherwise. This program was used to determine what a fin array would have to be in order to fulfill the goal conditions given to the optimizer. The length, thickness, number of fins must be within specific bounds given by the user. In order to show that the program operates as intended, the example problem from a screencast was used. The goal condition given was to achieve an overall effectiveness that was as close as possible to the one given in the example problem. The first time the program ran, it returned the same length, thickness, and number of fins that the example problem gave. The second time it ran, it returned a different length, thickness, and number of fins. These numbers happen to achieve the same overall effectiveness as the first run. This shows that the program can create multiple fin arrays that will fulfill the same goal conditions. If this were to be used in a real-world setting, a company could use this to create different fin arrays that would perform the same function and possibly be easier to produce. This program is not limited to just solving fin arrays. If the user were to provide the functions necessary, then it could optimize anything. For example, the user could optimize a bridge to have the least amount of stress at a particular point, while using the least amount of material possible. Or the user could optimize the efficiency of a motor by changing the size of the piston, material properties, and fuel types. The optimizer determines the best fin array by testing several different fin arrays and their children against the given goal conditions until one is determined to be the best. The program was able to replicate a screencast problem by using this process of natural selection. It was able to provide an alternative fin array that would accomplish the same thing.